So I'm going to show that if you have a linear transformation from V to W, T is invertible if and only if T is 1 to 1 and non-2. Now let me remind you what T invertible means if and only if there is an S from W to V such that if you do first S and then T and then S of W equals W for all W belonging to W, and S of T of V is equal to V for all V belonging to V. In other words, they just completely undo each other. At first you mess with the W by doing something with S, and then do T, you undo each other. So you think about these as adding and subtraction, right? S maybe adds 3 to W, and then T would subtract 3, and so you're left with something just the same. So what we're saying here is that it's invertible if and only if it's 1 to 1 and non-2, which means that you have this, you can find a map S, or if you can find a map S like so, then T is 1 to 1 and non-2, and if it's 1 to 1 and non-2, you'll be able to find a map S. So I'm going to prove this, and it's an if and only if, so I need to prove two different things. I'm going to prove this maybe the second direction first. I'm going to suppose T, which is linear, is 1 to 1 and onto. You know what? Scratch that. I'm going to do the other direction first, because it's a little bit easier. Suppose T is invertible. So there is an S as above, right here. Now suppose A and B belong to the inputs such that T of A equals T of B. I'm checking 1 to 1 here. This is the standard way to show that something is 1 to 1 is suppose that you have two inputs here that produce the same output. The output is called T of A and T of B. They're the two outputs and they're equal, so they're really just one output. Do I have just one input or do I have two? Well, what I can do is I can take S of both sides. If these two things really are equal, then I should be able to stick them both in S and get the same result, because S is a function. And that means that I get ST of A is equal to ST of B, but as above, STV doesn't change anything. So A is equal to B. So T is 1 to 1. Why is that? Because if I have two different inputs, A and B, that produce the same output, T of A is equal to T of B, the output is T of A or T of B, I have two different names for it, then it has to be that the two inputs were the same. So each output, called T of A, just has one input. If you think it has a second one, B, that means that the two inputs are really the same and you're wrong. And now I'm going to show that B is onto. That T is onto, sorry. And the standard way you do that is you let W belong to W. I'm going to find a V such that T of V is equal to W. Then I need to show that T of something is equal to W. And here's what that something is. It's S of W. It's invertible, so I have this function S. I'm going to use it because S equal to T S of W, which equals to, well, TS of W is always equal to W, so that's just a really long equal sign, so it equals W. So T is onto. How do I find the thing to put in there? If I want to get W, how do I find out what to put in there? Put in S of W. So T is 1 to 1 and onto, so I've done this direction. Now I'm going to go the other direction. I'm going to define a function S. So I'm going to let, how about W belong to W? And since T is onto, there is a v belong to v such that t of v equals w. Because t is 1 to 1, this v is unique. It is the only way to get w back. So the way I'm going to do is I'm going to define s of w equals v. So we have defined an s that maps from w to v. But so what I've done is I've shown that there is a function s from w to v, but I need to show that both of these things hold. Let w belong to w, such that s of w is equal to v. Then t of s of w, I want this to be w, but I need to follow the rules I've set up here, is equal to t of s of w by definition of composition. What's s of w? Oh, I defined s of w to be v. What's t of v? Well, remember how I defined s of w? S of w equals v comes from the fact that t of v equals w. So by the definition of s, how do I find out what s of w is equal to? Well, s of w equals v if and only if t of v equals w. So it equals w by basically this relationship. And now I can let v belong to v such that t of v equals w. Then I'm going to look at the map st of v. Well, by definition of composition, it's t of like so, which equals s of w by this. But how do I find s of w? S of w is equal to v, where v is exactly this relationship, so this has to have been v. So s is the inverse of t. So t is invertible. So what have I done? If I assume that t is invertible, in other words, if I assume that there's this map S, then I automatically know that t is 1 to 1 and t is onto. On the other hand, if I assume that t is onto and t is 1 to 1, then I get that t is invertible. Oh, by the way, I should really specify, t is 1 to 1 allows this to be a function. If it's not 1 to 1, you might not get a function, because for instance, you might have several different v's that give you t of v equals w. Because 1 to 1 means that for every output, you have at most one input. Maybe you have exactly one input if you define your domains carefully. If it's not 1 to 1, that means you can have multiple v's equaling w. But that means, so if you have t of v1 equal w and t of v2 equal w, and they're not the same, then s of w would be equal to v1 and it would equal v2. That means it's not a function, because it would fail the vertical line test. Because it would have two outputs for the same input, and you won't know what the output is. So that is all. I've proved this. We're done.